This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we're delving into the archive paper Multi-Head RAG, Solving Multi-Aspect Problems with LLMs. This paper proposes a novel approach to retrieval augmented generation, RAG, focusing on handling queries that require retrieving multiple documents with significantly different content. Let's start with the core problem this paper addresses. What are the limitations of existing RAG solutions when dealing with multi-aspect queries?
Existing RAG methods often struggle with queries demanding diverse information. The embeddings of documents addressing different aspects of a query can be distant in the embedding space, hindering effective retrieval. A simple example, what car did Alexander the Great drive, requires retrieving documents on Alexander the Great and the history of automobiles, two very different topics with potentially distant embeddings. This limitation extends to complex real-world scenarios, such as analyzing industrial accidents, where relevant documents might cover worker profiles, equipment records, maintenance logs, and weather data.
So the challenge isn't just about retrieving relevant information, but about retrieving relevant information from disparate sources. How does multi-head RAG, MRAG, address this challenge?
MRAG's core innovation lies in leveraging the multi-head attention mechanism within transformer models. Instead of using the final decoder layer's activations as embeddings, standard RAG, MRAG utilizes the activations from each individual attention head within the multi-head attention layer. The hypothesis is that different attention heads capture different aspects of the input data.
That's an elegant solution. Can you elaborate on how these multi-aspect embeddings are generated and used in the RAG pipeline?
The pipeline involves two stages: data preparation and query execution. During preparation, each document chunk is encoded and multiple embeddings are generated, one per attention head forming a multi-aspect embedding. These are stored in a vector database. During query execution, the query is similarly encoded into a multi-aspect embedding. Retrieval then involves finding the nearest neighbor multi-aspect embeddings in the database, considering all heads.
The paper mentions a voting strategy to combine results from different attention heads. Can you explain the rationale and mechanics of this strategy?
The voting strategy accounts for the varying importance of different attention heads. An importance score is pre-computed for each head, considering both the average L2 norm of its embeddings, reflecting attention weight, and the average cosine distance between embeddings, reflecting spread. During retrieval, each head's top take results are weighted by this score, and their rank, with higher ranked, higher scoring heads having more influence.
The paper presents a comprehensive evaluation methodology. What data sets and metrics were used to assess MRAG's performance?
The evaluation involves synthetic data sets generated from Wikipedia articles, categorized into different topics. Queries were created to require retrieval of documents from multiple distinct categories. Metrics included retrieval success ratio, exact document matches, category retrieval success ratio, matches within the correct category, and a weighted combination of both.
What were the key findings of the evaluation? How did MRAG compare to standard RAG baselines?
MRAG consistently outperformed standard RAG, showing improvements of up to 20% in the weighted retrieval success ratio, particularly for queries with multiple aspects. The improvement was more pronounced for category matches than exact document matches, highlighting MRAG's ability to retrieve relevant information even when the exact document isn't perfectly matched. Furthermore, MRAG performed comparably to standard RAG on single-aspect queries, indicating no significant performance penalty for simpler tasks.
The paper also explores integrating MRAG with other RAG techniques, such as Fusion RAG. What were the results of these combined approaches?
Combining MRAG with Fusion RAG, which uses an LLM to generate refined queries, further improved retrieval accuracy. Fusion MRAG consistently outperformed both Fusion RAG and MRAG alone, demonstrating the synergistic potential of these methods. However, this comes at the cost of increased computational resources and token usage.
The paper also investigates the impact of using embeddings from different decoder blocks and different voting strategies. What were the key takeaways from these analyses?
Experiments showed that using embeddings from the last multi-head attention layer yielded the best results. Alternative voting strategies, while explored, did not outperform the proposed weighted voting scheme, validating the design choices.
The paper concludes by highlighting MRAG's potential for real-world applications. Can you briefly summarize the real-world use cases discussed?
The paper showcased MRAG's effectiveness in two real-world scenarios: legal document synthesis and analysis of industrial accident causes. In both cases, MRAG demonstrated superior retrieval performance compared to standard RAG, highlighting its applicability to diverse domains requiring multi-aspect information retrieval.
What are the key advantages of MRAG compared to existing RAG approaches?
MRAG offers several key advantages. It effectively handles multi-aspect queries by leveraging the inherent multifaceted nature of multi-head attention. It's computationally efficient, requiring no additional LLM queries or increased storage, and it's easily integrated into existing RAG frameworks.
Are there any limitations or future research directions stemming from this work?
While MRAG shows significant promise, further research could explore optimal strategies for assigning important scores to attention heads, investigating different embedding models and architectures, and extending the approach to handle even more complex query structures. The impact of the choice of embedding model also warrants further investigation.
The paper mentions the use of both synthetic and real-world datasets. How did the performance on these two types of data compare? Did the performance characteristics differ significantly?
While the paper primarily focuses on the synthetic dataset for a controlled evaluation, the real-world datasets demonstrate the practical applicability and effectiveness of MRAG in diverse scenarios. The consistent performance improvements across both types of data suggest that MRAG's benefits are not limited to specific data distributions. Further research could explore the generalizability of MRAG across a wider range of real-world datasets and tasks.
The paper highlights the importance of the choice of embedding model. Could you elaborate on this aspect and its potential impact on MRAG's performance?
The choice of embedding models significantly influences the quality of the generated embeddings and, consequently, the performance of MRAG. The paper demonstrates the effectiveness of MRAG using two different embedding models, SFR and E5, both showing consistent improvements over standard RAG. However, exploring a broader range of embedding models and investigating the relationship between model characteristics and MRAG's performance would be beneficial for future research. This could lead to guidelines for selecting the most suitable embedding model for specific applications.
The paper mentions the use of a vector database. What are the implications of the choice of vector database and its indexing strategy on the efficiency and scalability of MRAG?
The choice of vector database and its indexing strategy directly impacts the efficiency and scalability of MRAG. The paper highlights the orthogonality of MRAG to the choice of database and NN search approach, implying that MRAG can be seamlessly integrated with various existing solutions. However, the optimal choice of database and indexing technique will depend on factors such as the size of the dataset, the dimensionality of the embeddings, and the desired query latency. Future research could investigate the impact of different database and indexing choices on MRAG's performance and scalability.
The paper emphasizes the seamless integration of MRAG with existing RAG frameworks and benchmarking tools. Can you elaborate on the practical implications of this aspect?
The seamless integration of MRAG with existing RAG frameworks and benchmarking tools like RAGS significantly simplifies its adoption and evaluation. This allows researchers and practitioners to easily incorporate MRAG into their existing workflows and compare its performance against established baselines. This ease of integration promotes wider adoption and facilitates further research and development in the field of RAG.
The paper mentions the use of a synthetic query generator. How does this contribute to the robustness and generalizability of the evaluation results?
The use of a synthetic query generator allows for the creation of a large and diverse set of queries with controlled characteristics, ensuring a comprehensive evaluation of MRAG's performance across various scenarios. This controlled environment helps to isolate the impact of MRAG's design choices and reduces the influence of confounding factors present in real-world datasets. The synthetic query generator contributes to the robustness and generalizability of the evaluation results by providing a standardized and repeatable evaluation process.
The paper discusses the computational cost and energy efficiency of MRAG. Can you elaborate on these aspects and their significance?
MRAG is designed to be computationally efficient and energy efficient, avoiding the need for additional LLM queries, multiple model instances, increased storage, or multiple inference passes over the embedding model. This efficiency is a significant advantage, particularly for large-scale applications where computational resources are limited. The reduced computational cost and energy consumption contribute to the practical feasibility and sustainability of MRAG.
The paper mentions several related works in the field of RAG. How does MRAG differentiate itself from these existing approaches?
While many RAG schemes focus on improving retrieval accuracy through various techniques, MRAG uniquely addresses the challenge of multi-aspect queries by leveraging the multi-head attention mechanism. Unlike approaches that rely on complex pre-processing or post-processing steps, MRAG achieves improved retrieval accuracy with minimal additional computational overhead. Its simplicity and ease of integration with existing frameworks distinguish it from other more complex methods.
The paper concludes by emphasizing MRAG's potential to democratize access to accurate and relevant outputs from LLMs. Can you elaborate on this aspect and its broader implications?
By effectively addressing the challenge of multi-aspect queries, MRAG enhances the reliability and accuracy of LLM-based applications across various domains. This improved accuracy and efficiency contribute to the democratization of access to LLMs, making them more accessible and useful for a wider range of users and applications. This has significant implications for various industries, including those dealing with complex data analysis and decision-making processes.
This has been a very informative discussion on multi-head RAG. Thank you.